We have seen how the motion of electrons around the nucleus are quantized. How then does this affect the behavior of a molecule? First of all, as mentioned, orbital energy is quantized. The energy difference between two orbitals is fixed. This is true for atomic and molecular orbitals. Electron behavior, as you saw, is defined by 4 quantum numbers. N defines the potential energy between the electron and the nucleus. L and m sub L define the energy of motion in orbits, which generates angular momentum. M subscript S defines the internal inherent angular momentum of a particle. Through the particle in the box, you also saw the size of quantum effects are inversely proportional to the mass. All energy, and hence all motion, is quantized. However, as particle size increases, the energy difference between states decreases. Therefore, for macroscopic particles, such as yourself or a baseball, energy and motion appear to be a continuum. Significantly, molecules are the largest particles in which the quantumization of energy is still observable. Molecular electronic transitions are still quantized as they are in atoms. And for the overall molecule, bond vibrations and rotational motion are also quantized. These facts serve as the basis for spectroscopy. We will now start our investigation of molecular motion through looking at bond vibration in detail, through a model known as the harmonic oscillator. Bonds are not rigid, they vibrate. This is because they are formed by combining electron wave functions which themselves oscillate. This motion can therefore be approximated by a spring, which is governed classically by Hooke's law. The potential energy V is equal to kx squared. In the case of a spring, kinetic and potential energy are constantly exchanged, with the net state being 0. Force, which as you know is mass times acceleration, or mass times the second derivative of distance versus time, translates to x, the position of the spring, equaling A times k divided by m to the 1/2 times t plus b. In this treatment, A is the amplitude of the wave, and k is known as the spring constant. The vibrational frequency of the spring, nu, is equal to 1/2 pi times k over m to the 1/2. Energy is related to the amplitude of the motion, with the energy equal to 1/2 ka squared. And you find Hooke's law defines a parabola. Whereas mentioned, the average position of the spring, or the average displacement of the spring at any given time, is 0. And therefore, the average energy as the spring moves back and forth in its oscillation is also 0. Having set the parameters for the harmonic oscillator, we now move to try to solve it quantum mechanically. In this case, the Hamiltonian now contains a potential, where h is equal to minus h squared over 8 pi squared m, the second derivative of the wave function, plus a new potential, 1/2 kx squared. However, the Schrödinger equation, h psi is equal to E psi, is now solvable. The solution one gets is that vibrational energy is equal to V plus a half h nu. This solution, minus the details, shows that vibrational energy itself is quantized, where V, in this case, is any integer greater than or equal to 0. This leads to a state where the energy levels wind up being evenly spaced at every 1/2, 1.5, 2.5, 3.5, and so on h nu, with the difference between each one being 1 h nu. Additionally, there is what is known as a 0-point energy. At the point when no external energy is involved at all, a bond will still vibrate and still have an energy of 1/2 h nu. The harmonic oscillator is modified through something known as the Morse potential. This modification is designed to fit the harmonic oscillator to the physical reality of a molecule. For example, a bond is a two-particle problem. The spring connects a mass of A and a mass of B, as opposed to in the harmonic oscillator. The vibrational frequency, nu0, now modifies to 1/2 k over nu to the 1/2, where nu is known as the reduced mass and is calculated by the mass of A times the mass of B divided by the mass of A plus the mass of B. Additionally, the well must remain in the first quadrant because we are now dealing in polar coordinates. MA and MB cannot both be at 0. They cannot both be at the same place at the same time. And the bond cannot be infinitely long. So you wind up with the shape of the Morse potential, which is defined as a function of the radius. V sub r is equal to d sub e, 1 minus e to the minus alpha r sub e minus r squared, minus, again, d sub e, where d sub e is known as the spectroscopic bond dissociation energy, r sub e is the equilibrium bond length. Energy is still quantized. However, the distances between the different energy levels is no longer evenly spaced. We now look into molecular rotations through a model known as the rigid rotor. In this case, this is an approximation of a diatomic molecule where you have two masses, Ma and Mb. They are connected by a rigid bond of length d. This molecule will rotate around the center of mass. In this case, all energy of motion is expressed as angular momentum. The Schrödinger equation becomes L caret psi is equal to E sub L psi. The energy, E sub L, is solvable without the details again. E sub L is equal to a new number, J times J plus 1, times H squared over 8 pi squared D. J, the new number, is called the rotational quantum number. It once again can have all integer values greater than or equal to 0. B equals H h squared over 8 pi squared d is called the rotational constant. In this case, I is known as the moment of inertia and has a value of I equals the reduced mass mu times d squared.